and I'll try to do a little faster than yesterday. So that's your time. All right, thank you. Hello, everyone. Jim Malis here. Let's talk about the old practice exam number 3, and let's kind of take it from there when we're doing this stuff. I guess there's a number of things you can do and say. I'm trying to debate with myself how to actually approach some of the stuff that you're looking at. Let me see what I can actually say regarding this stuff, guys. That might be able to help us out, and let's see how we can take it from there. Let me go, let me do hopefully a good number of problems for you guys, a decent number of problems. And I can always hook this around when I do the practice exam, the old practice exam for the final exam. The old practice exam for the final exam, I can maybe tie up some loose ends that we had as well that has from the first 3 old practice exams that are going on there. We talked about a number of things, so let's kind of keep talking, I guess you could say. We talked about the laws of exponents and some things that are very important in that regard. And we said if you were going to multiply 2 exponentiated quantities with the same base, you're adding exponents. If you're dividing 2 exponentiated quantities with the same base, you're subtracting exponents. If you're exponentiating an exponentiated quantity, you're multiplying exponents. If you are taking something to a negative power, it's 1 over that quantity to a positive power. Or if it's to a positive power, you can make it 1 over something to a negative power. It doesn't matter. If you had x to the negative 3, that's the same as 1 over x to the positive 3. But if you had x to the positive 3, you could write that as 1 divided by 1 over x to the negative 3. I'm sorry. You could write that as 1 divided by x to the 3. What's a fraction divided by another fraction? It's the first fraction multiplied by the reciprocal of the second fraction doing the dividing. Well, what is that right there? That 1 over x to the 3, 1 over x to the 3 is x to the negative 3. So if you got it under here, if you move them up, you got positive. If you got it under here, you move it up, it's negative. It doesn't really matter. The big thing, this reality holds regardless of the sign. If you're exponentiating something to a particular power, that's the same as 1 over that same exact quantity exponentiated to the opposite of the power that you had to begin with. The exponentiation x to the 3 is the same as 1 over x to the negative 3. X to the negative 3 is 1 over x to the positive 3. So, okay, so it works out that way. Something to kind of look at in that regard. So we talked about some of that stuff, you guys. See what we can say beyond that, I guess you could say. Trying to give you guys these I'm kind of debating with myself maybe a more efficient way to do this. The last time I did it, the video was between 3 and 4 hours long, about more than 3.5 hours long. So on occasion it gets that way. If it happens, it happens. I mean, you guys, we're there for you guys. We're trying to help you out, so it's going to help you. Just look at the stuff at your convenience, at your pace, and we'll figure out what the heck we're doing. All right, so we've got that. We said a lot of, we say a lot of stuff regarding this stuff, you guys. You can also say, you had this to the n power, it's this. If you had this to the n power, it's this. If you mix and match it, if it was something like this, as long as it's straight out multiplication and or division going on only, all of this holds. If there's addition and or subtraction going on within the brackets or parentheses, it's not as easy. You've got to use the multinomial theorem in circumstances like that. You've got to use the binomial theorem in circumstances like that. So, basically, you guys, that's it. I mean, this tells you a whole lot when we're doing this, and you know, there's more to come, I guess you could say. This stuff works. These exponents don't have to be the nice natural numbers, 1, 2, 3, 4, or even the whole numbers, 0, 1, 2, 3, 4. They can be fractions, they can be decimals, they can be a lot of stuff. Kind of getting into that. Let me kind of throw a whole lot at you in a real kind of super condensed lecture in a sense, and then show you some of the problems whenever we show the problems. Maybe the next time I can show it when I'm doing the practice final exam, the old practice final exam, I can hook around and do some of that stuff with reference to what I'm doing here. We'll see how that all works out. Let's talk. If n is a natural number, let's say, if you have x to the 1 over n, that means the nth root. That means the nth root of x. It does not mean the same thing as this. This thing right here means all of this. All of this is underneath the 1. Here, it just means that. These are two different things, so don't ever confuse that. Don't ever confuse that when you got that. X to the 1 over n is equal to the nth root of x. X to the negative 1 over n. Based on what I've been saying, guys, where do you think that's going to go as we do this? So let's see what we got here. X to the negative 1 over n is 1 over the nth root of x. So on and so forth. So not too bad. Not too bad. Now let's talk. I mean, the devil's always in the detail, I guess you could say. So if you had x to the 1/5 power, that means the 5th root of x. If you had x to the negative 1/5 power, that means 1 over the 5th root of x. You got this. You got this. Look at something like that. Now, I cannot emphasize how important this aspect right here, of the laws of exponents is. If you exponentiate, and there's so much that goes into this, guys. I wish I was, first and foremost, I wish I was meeting you guys in person. One day we will, I hope, okay? Right now, that's not the reality we're dealing with. When we're dealing with, at least at the time that I'm writing this, at the time that we're copying this, right? Subsequent times, if this file is used, hopefully that's all done, you know. But there's so much here, guys. There's so much here. I wish we could talk more, you know, on this stuff. There's a whole lot more that, and I think the in person kind of lends itself more carefully to it. All right, we'll look at it right now and give me an idea of what you think. That thing over there is pretty important. In other words, if you got anything And let's put it this way. Let's say you had a to the a power and the whole thing taken to the b power. And a and b are not integers necessarily. They're any real number. They can be irrational numbers, they can be rational numbers, they can be any real number. Well, I can approximate what's going on by using a ratio of two integers. A ratio of two integers, I can approximate any real number. First of all, I can get any real number, and if I can't get all the real numbers, and actually I cannot get all the real numbers with a ratio of two integers, because what did we say? The integers are, the irrational numbers are not a ratio of two integers, but I can approximate any irrational number to any degree of accuracy that I wish using rational numbers, using a ratio of two integers. If you're talking about this, I've got a question to ask you. That's a times b. Yeah, I got another question to ask you. Could you put the b right here and the a on the outside? And then you got x to the b times a, which is x to the a times b. Fascinating. Okay, let's talk more. Let's say you had, and we're saying some stuff here. We said what we said here. Let's use this reality to kind of talk a little bit. And it's going to help us later on with these things they call logarithms. Okay. What if? And this is going to help us with a lot of this stuff, you guys. What if I had x to the m over n, where m and n are any integers except for 0. They both can't. You can have the top guy equal to 0, and 0 divided by a non-zero integer is 0, and x to the 0 is just 1. X to the 0 is just 1. Let me not worry too much about this right now. I'll deal with positive integers right now. And later on, I can throw negative integers in there if I want. If I want something to make it negative. But let's say m over n is a positive quantity. I do got to ask you a couple questions related to it. Is it true? Well, m over n. Didn't I say that whenever you're exponentiating, I did it over here and I did it over here. When you're exponentiating an exponentiated quantity, you multiply exponents. So you got this. Is that a true story? Yeah, it is. What is m times 1 over n? It's m over n. Okay. Can I switch those around? Yeah, 1 over n times m is m over n. M times 1 over n is also m over n. M times 1 over n is the same as 1 over n times m. Interesting. What does that mean? That right there, did we say x to the 1 over n is the nth root of x? The nth root of x taken to the m power is the same as x to the m, then get the nth root. Watch this again now. the nth root of x, get an answer, and then go to the m power is the same as going x to the m power first and then getting the nth root. Hugely significant. If m and n were positive, if let's say they weren't, whatever, positive or not, if the ratio m over n is positive, then x to the negative m over n is negative. That would be equal to, what did we say? We said this. Then what did we say? Well, what is the bottom? We said a lot of stuff. We could say at this point, this means x to the 1 over n, the whole thing to the m. The other one is 1 over x to the m to the 1 over n. So what do we got here? Again, we said this. We said it comes out to this. That's not a big deal. I'm not going to change that. I'm going to change right here. The nth root of x to the m power. The nth root of x to the m also works. And again, guys, I'm not saying anything too profound here. For some reason, I didn't erase this. It's a little wet over here, so it's not going to give you right as well as it should. Let's try that again. We got x to the m. Still an issue. Okay. All right, guys, you got me. I don't know why it's not writing. Let me go over here. It might just be done, I think. Yeah, it's done. All right, let's try it again here. I am sorry. I always go through about 20 of these every time I talk. All right, everyone. I'm nailing shots from 20 feet out, okay? You just can't see them. Let's try this. It might work for just a little bit. X to the m, the nth root of that. Okay. Pretty big time stuff, guys. This stuff is immensely useful. It's going to help us it's going to help us later on when we talk about logarithms and how they relate and how we can do some stuff, and we'll see how I'm going to do this. But this is pretty important stuff in this regard. Pretty important stuff. In any sort of science that you're doing, it's good to have a strong idea of the do's and don'ts. The more that you know, the more you can handle a lot of things. Very important. So leave that, I'll leave that there for a while. I wish I could leave it up the whole time, actually, to be honest with you. Wish we could have it somewhere, just slide it back here to us, but you got it on the film. So make sure you use it. This is immensely useful stuff in economics, in other mathematics, in physics, in chemistry, you name it. I mean, in engineering, you can find this stuff useful. So the mathematics is good in that regard. Okay, so we got all this, and that's going to help us do some problems. I mean, I'm probably going to hook it around and see how I can actually do problems and stuff like that regarding something like this. kind of moving around with some of this stuff, guys. There were a few things. There were a few things. The way some of these problems were put together was not right. So we'll have to figure out how we're going to do it. Most of them, overwhelmingly, are done quite good. And on occasion, people make mistakes. I do it all the time, so it's not something I'm going to condemn somebody for. Talk some more, I guess, related to this stuff. There is, how do you handle roots and stuff of that nature? And I said you can use them as exponents and stuff like that. Usually when you're dealing with roots, and somewhere I'm getting into roots. You can see I'm getting into roots down here. I'm getting into roots over here. When you're dealing with roots, they don't want you to divide by the root of something if that root is an irrational number. They want it rationalized. They want everything on top, on the numerator, somehow written, and the denominator has something that is, the denominator is not an irrational number, not a square root, not a cube root, not something, that's kind of left unresolved, or a fourth root, or whatever kind of root it is. They don't like radicals on the bottom. Now, so you can kind of argue some of the stuff of how they're doing this, but let me kind of see exactly where I want to go with this, I guess. It's a horse apiece in some of these, how to do some of this. They've got something else, and I'll kind of hook around and do some of this stuff. We deal with the real number system. The real number system is everything that is on the horizontal line. X equals 0, 1, 2, 3, -1. Yeah, but everything in between. Not just 0, -1, -2, -3. Not just, 0, -1, -2, -3, 1, 2, 3, 4. Everything in between there. That's all the real numbers. That's something they deal with. It's a real number system. Well, they expand the number system beyond the real number system. It is mathematically useful, and they expand the real number system to the complex number system. The real number system belongs to the complex number system. The complex number system is, rather than the straight line, it is everything on this plane. In other words, this is 0, this is 1, 2, 3, etc. -1, -2, -3. And then they got this thing called I. 1I, 2I, 3I, going to infinity. -1I, -2I, -3I. And so you go, there's a real part and there's an imaginary part. The imaginary part has I. Now you might want to ask, yeah, what is this I you just introduced? Okay, and how does this whole thing work? Well, the real number, the complex numbers are all composed of a real part plus a real part times an imaginary part. So this is imaginary, purely imaginary. They call it imaginary, purely imaginary, and this is real. The real plus the imaginary gives you the complex numbers. Again, I didn't answer what I was. I is defined as the square root of -1. The square root of 1 is 1. The square root of -1 is not to be found in the real number system. So they make up essentially a number system that would include the square root of -1. This is very useful mathematically, believe it or not. While they're making up numbers, yeah, I know. The numbers they make, though, they can use it for aeronautical engineering. They can use it for electrical engineering. They can use it when they discuss trigonometry, if you want to believe any of that. I mean, but it's true. It's totally true. So as long as they're mathematically consistent, there's this thing called analytic continuation. Analytic continuation means you can kind of like move it to like another, you can move a lot of the mathematics to another number system, and if you're consistent with it, there's a chance, and in this circumstance there is, a lot of application. There's a lot of application that can come into, that can happen. So I equals the square root of -1 is that. So if this, what's the number -2 plus 3i? Well, here's -2. Here's, or -2 plus 1i, let's say. -2, let's go -2 plus -3i. -2, here's 3i right here. And that vector, that directed line segment is the point. Whereas over here, the point was only on the x-axis. Here, it's associated with the x-axis and the y-axis. I equals the square root of -1. So, some pretty interesting stuff that happens regarding this, and there's some real amazing application that goes on. I'll talk a bit about it, and then we'll see what else we can say. Going to try to throw hopefully a lot of the basics at you. And then hook around and hit some of these, and then probably come back and maybe emphasize a good part, the old practice exam. Come back and emphasize the old part of the old practice exam number 3 when I do the review for the final exam. So I can at least give you a little bit of a start here, and then we'll come and do some other stuff later. All the stuff should be there for you if you look at all the videos. The lion's share of everything that you're going to need is in these videos that I've shown you. But you got to look at them. You got to look at them well, you got to study them, and you got to look at other stuff that I'm going to try to present to you guys. So let me okay. So, they made the complex. Now, this is an interesting point now. If this is a real number, and that's a real number, but you multiply it by I, it's a purely imaginary number. If you add the two, I already told you this is what the complex numbers look like. Now, if B is equal to 0, 0 times I is 0, it just becomes A right here. So, the real numbers are a subset of the complex numbers. That's one thing to look at. How do you actually do some of this stuff that we're going to be doing? Well, I mean, if you had A plus BI, and you were going to multiply, let's say A plus BI plus C plus DI, how do you add these? If you add, subtract, exponentiate, multiply, divide, you name it, any complex numbers, you are within the complex numbers regarding your answer. Your answers are going to stay within the complex number system when you deal with complex numbers. This stuff's incredibly useful. Now, let's kind of backtrack a little bit. We just defined I to be the square root of -1. If you take and square I, you are square rooting -1. The square root of something squared gets you back to where you started. So I equals the square root of -1. I squared equals -1. I to the third is I squared times I. Now we just said that I squared was -1, so it's -1 times I. And I to the fourth is I squared times I squared, which is -1 times -1, which is 1. It comes full circle. And that'll just keep rotating around you guys. So what do you got here? I mean, you got this, you got basically that I equals I squared equals -1, I to the third equals -I, or -1I, and I to the fourth equals 1. You got I, -1, -I, and 1. What's going on here? Well, let's draw our thing here again. This is 1. This is length from 0 to 1. Right here, length 1. From here, this is 0 to I. This right here is 0 to -I. And this right here, forgive me, not true. This is -1 rather. And right down here, this is 0 to -I. I have not drawn this very well, but I do want to make a very important point. This arm length, this arm length, that arm length, and that arm length, and that arm length are all the same length. The magnitude, it's kind of a mathematical, the magnitude of the number 1 is equal to the magnitude of the number -1, is equal to the magnitude of I, is equal to the magnitude of -I. Sometimes they don't put 2 goalposts like that. They just put 1, and they make it look like an absolute value symbol. The magnitude of 1 is equal to the magnitude of -1, is equal to the magnitude of I, is equal to the magnitude of -I. The length of this leg, the length of that leg, the length of that leg, and the length of that leg are all equal. The measuring stick of practically everything, to my knowledge, and I don't know everything, other people know a lot more than I'm ever going to know. Everything I've seen, the measuring stick of all that goes on in mathematics is that distance from 0 to 1. Right here. That distance from 0 to 1. And they're all the same length, as we said, right? That distance from 0 to 1 is the measuring, and they're all the same length. All the fractions, all the decimals, the negative numbers, the positive numbers, I can construct the complex numbers by using this measuring stick from 0 to 1. How big is the distance from 0 to 1? Don't be surprised, it's 1. That distance from 0 to 1, 1 is the measuring stick. If you break up the distance from 0 to 1 into small pieces, you got fractions. If you multiply them in particular ways, you got mixed numbers, you can get decimals. If you multiply by a -1 or a negative number, it goes the other way on the line, on the number line. There's a lot that goes on, you guys. Notice on this thing, and this thing just rotates. Round and round pretty much. Goes this way. When you're exponentiating, doing a positive exponent. There's a lot that happens here, guys. There's a very important number later on, e, the base of the natural logarithm. For the exponential function, they go e to the I theta sometimes, e to the I theta, and this is the analytic continuation that we talk about. The cosine of theta plus I times the sine of theta is equal to this. It's more or less made up, so to speak, but it's mathematically consistent. And the conclusions are amazing. They are simply amazing. That goes on. This is e to the I theta equals cosine theta plus I sine theta. You can do this and prove it using this thing called the multinomial theorem. The binomial theorem is something we prove when we exponentiate quantities that have an addition or subtraction in them. And there's a lot of, and if there's a lot of terms within the quantity and we're exponentiating, we don't use the special case of the theorem I'm about to use. The binomial theorem is for two things. If you do it for many, many things, use the multinomial theorem. The binomial theorem is a special case of the multinomial theorem. And you can prove this. Mathematically, it's consistent. The conclusions are phenomenal. You can use them in all kinds of engineering. Aeronautical engineering, electrical engineering, believe it or not, it's everywhere, even though it's based on kind of a made-up number. Mathematically, you can do a lot and work with it. It's not really our business, but I figure I'd tell you that. That I is there, but man, it's immensely important. It's immensely important. If that's the case, let's look at some things that happen. If you were adding two complex numbers, all that you do is add the real parts together and then add the imaginary parts together and multiply by I. Notice it still looks like real part plus imaginary part. Okay? It still means it's still real part plus imaginary part when we do something like this. Okay? When you subtract, the same kind of thing happens. If you were gonna do subtraction, you subtract the real parts, you subtract the imaginary parts, and it comes out to that. If you were to multiply two of them, I think this is probably a good way to do it. When we look at this stuff, you can see what conclusions we're arriving at. So let's see what we can say. Okay. If you're multiplying two exponentiated quantities, you got A plus BI times times C plus DI. Pretend you are just dealing with the letters that you know how to do. Don't forget though, as we do this, it's always in the back of your mind that I is by definition the square root of -1. I squared, I equals the square root of -1, I squared equals -1. So always have this. Always have this. Let's FOIL it out, guys. Take the A and go here. Take the BI and go here. Let's take our time, let's see what happens. We got AC plus ADI. Then we got BIC, which is BCI. Then we got BI times DI. AC, The i's right here. Why don't you factor the I out? Okay. Watch out here, guys. What's B times D? Notice you're not distributing anymore. Why? There's no addition or subtraction within the quantities after you've done the distribution. Here we did the distribution. Yeah, because there's a plus here. Here we don't. Notice how this stuff builds up. It only helps if we look at it, if we try to figure out what we're doing here. All right. I times I. Yeah, we talked about that too. I times I is I squared. That's -1. What just happened here? What happened is you got AC plus a -1 BD, which is the same as minus BD, plus AD plus BC times I. This is real. This is imaginary. It's of this format, real plus imaginary. Even when you multiply, not an issue. No matter how much you exponentiate something, you're going to get a real plus imaginary when you're dealing with the complex numbers. There's this thing called closure. Whatever operations you do within the complex numbers, stay within the complex numbers. As simple as that. For our purposes of what we're doing here. Okay. So that's that. Now, it can get a little interesting. That's good. That's fine. Take this guy, and good luck. How are you going to divide? It's not like dividing by 3 is easy. 27 divided by 3 is 9. 81 divided by 3 is 27. 300 divided by 3 is 100. Yeah, it's all easy. You divide by 3, divide by 3, divide by -3. Here you're dividing by 5 plus 3i. If this was 5 plus 3i, how the heck are you going to do it? You know? When you look at some of this stuff. So let's see. Well, how are you going to do it? They don't want complex numbers in the denominator. They don't like radicals in the denominator, like the square root of 3 or something like that. You got to kind of figure out a way to get rid of it. We'll talk about that as we have time to talk about it. We'll figure out how to talk about it. So you got this guy right here. So let's see what we got. What they want you to do is, if this guy is a number, it's a complex number. Its complex conjugate is identical to it, but instead of an addition, there's a subtraction here. Those two things are complex conjugates. Complex conjugates are, if one is A plus BI, the other one's A minus BI. To actually solve this right here, you got to multiply by a weird-looking special 1. You're using the complex conjugate of the denominator, and you're using that as your special 1. You're probably wondering, okay, why is he doing that? Because it guarantees you that the bottom will knock out the purely complex numbers. They'll make it just into a real number. You'll see what I mean. C plus DI times C minus DI. You guys remember back in the day we talked about the quantity A plus B times the quantity A minus B, and we got A squared minus B squared. Well, this guy becomes the A, this becomes the B, here's the A again, here's the B again. So according to that logic, if you grind this out, you can also just do these guys and pretend you're just dealing with letters. And then at the end, kind of be aware of the reality that I is the square root of -1 and I squared is equal to -1. You got C squared minus the quantity di squared. Remember, it's a squared minus b squared. Let's talk. Square the d, square the I. Let's keep going. It's -1. So, what do you got? Minus a negative d squared. Minus a minus is plus, c squared plus d squared. Interesting. If you actually did it up here, if you actually took a plus bi and multiplied by its complex conjugate, you'd get a squared plus b squared. And that's actually the magnitude, of the complex number squared. If you square root a squared plus b squared, yeah, it does look like c squared equals a squared plus b squared. C squared equals a squared plus b squared, square root it. The c, the length of the hypotenuse, the length of the vector that I drew earlier, is going to be the square root of, the sum of the squares. The square root of a squared plus b squared. So it's looking like this. So you make, guys, do you change anything if you multiply by 1? No. I'm going to give it a different look, though. I'm going to give it a different look and not have a complex number on the bottom. I don't know what this is. It's not easy to visualize, but maybe you can visualize it. This and this are the same. Same divided by same. This divided by itself. This divided by itself is 1. Let me not get 1, though. It is 1, but let me not actually do it. Let me not do the ratio. Let's leave it. This divided by this is 1. Multiply by that special 1. A plus bi times c minus di. Multiply this across, and you get c squared plus d squared. Forgive me, I don't know how I got the b here. It should have been d. There it's b because the b is there. But you got this. This right here is a real number squared. A real number squared. Add a real number squared. Take a real number, square it. Take another real number, square it. Add them together, you've got a real number squared is a real number. A real number squared is a real number. Add them together, you got a real number. If you multiply these two out, let's see where it goes. And like I said, I think it'd be easier when we actually do some actual quote-unquote real numbers without the symbolism. Go more with just numbers that we're used to looking at. But you got something like this looking here. Let me just, since we got to here, let's keep going with what we got. Okay, let's see what we got. We said all that. You guys know all that, so we're not going to worry about it too much. Okay. So let's go with it, man. We're looking at this right here. How, let's see. This is the answer, but let's simplify that answer. So you're going a plus bi, c minus di. Minus di is plus a negative di. Let's FOIL this thing. You know how that goes. You're going to go here. You're going to go here. And you're going to go here. And you're going to go there. All right. Well, let's see what we got here. We got a times c. A times c. A times D times I, negative ADI, BI times C, CBI, BI times negative DI, see what we got here. We got AC, the I's right here, so you got, you know, I can write this a number of ways. I'm not sure what's the best way. They all mean the same thing, so we're not going to worry too much about it. B negative D is negative BD. I times I is negative 1. That's interesting. Negative 1 times negative BD is positive BD. So you got AC plus positive BD. That's a pure real number right there. And the other one, you got negative AD plus CB, the whole thing I, the whole thing over purely real number, purely complex number, purely real number, purely imaginary number, straight out complex number divided by a real number. Well, this just makes the vector smaller or bigger, whatever it's going to be, but it's always pure real plus pure imaginary, straight out complex number. Even the division, even this thing we did right here, even this right here, is yielding something looking like a complex number. Everything stays within the complex numbers when you deal with it. You know, it's not as difficult as you might think, guys. I mean, it's not. I mean, the way we did that. I mean, let's put some other numbers in there and maybe make it seem like it works out. Okay, that writes okay. Let's see if you guys can see that. Let's see. Prefer to use just the darker markers, to be honest with you guys, but. Let me see what I got. Okay. Let's say for this guy that we had right here, and we just solved it. We took this, and we just solved it right here. We got this. Okay? So we just solved all that. I didn't even need to throw that away. I just love making the baskets, man. It's just the way it is, okay? Just kidding. All right. Let's put something there. Let's figure out what we're going to do. Let's say you had 3 plus 5i divided by 7 plus 4i. How would you get an answer? I need to solve that. Here's the problem. Solve it. Good luck. Yeah. Why don't we just do what I just did? Let's multiply by a special one involving the complex conjugate of 7 plus 4i. Multiply this across. With that, just multiply it across. and then multiply this. This bottom guy is the difference of 2 squares. We've already kind of gone into that. You've got 3 plus 5i. Seven minus 4i. It's a difference of 2 squares, so it's 7 squared minus the quantity 4i squared. What are we talking about? Got this. Again, we said with the difference of 2 squares. Where did we do this? We did it right here. How it all played out. I mean, I erased it, but you saw how the whole thing plays. How the whole thing plays out. It becomes a squared plus b squared. Is that true? Yeah. Here's a, square it. Here's the b, and this is -1. When you square I, you get -1. -1 times square the 4, you get 16. Square the I, you get -1. -1 times 16 is -16. Negative minus -16 is plus 16. So what you end up getting is you get 49 plus 16. And that's good. I mean, we got to here. You add these together, you're going to get 65. And then here, minus this, plus the opposite. Take this, do the FOIL method. You end up going 3 times 7, 21. 3 times -4. 3 times -4i, rather. -12i. 5i times 7. Positive 35i. 5i times -4i. 5i times -4i. 5 times -4 is -20. I times I is -1. So it's -20 times -1. Okay? So what we get here, guys, go up here, guys. We got 21 plus -12i plus 35i -20 times -1 is 20. The bottom is 65. You know where this is going, guys. I mean, give myself a little bit more room. And again, it's just everything we did in a more symbolic fashion being shown right here, you guys. Got this. Surprised I didn't erase that. I do that a lot when I'm doing the erasing. Sometimes erase the most relevant portion of the whole problem. Luckily, you got it on film, guys. That's the big thing, I think. It'll help us out, I think, doing this. So let me think. I mean, okay, the big thing was, guys, I mean, when you did it here, you went 5i times -4i. And we figured that one out to be 5 times -4 is -20. I times I is -1. -1 times -20 is +20. That's where it's getting right there. Take the +20, the +21, add them together. They're both real numbers. The other guys go here. Looks good to me. Divided by 65. If you leave it like this, yeah, that's fine. I mean, I'm going to see how they do the evaluations, guys, on this stuff. As I'm doing this, it's late July, and I'm going to find out sometime in August exactly how they're doing some of this stuff. So, but I know the math is the math, so I just want you to know the math. You know, that's the big thing. That's why I'm doing something like this. For those of you that are in my intermediate algebra class, for those of you that are in my university physics class at UWM, I have a much stronger idea, obviously, of what I'm going to be doing. It's stuff I've done before in the past, so it's much stronger idea of what I'm doing. So this is fine. You're not going to, for those of you taking a physics class from me, you're not formally going to be seeing this, but all the mathematics you know is always going to help you. It's always in your toolbox that you can use and it'll let you help you out. If you go into engineering, if you go into chemistry, all the math that you know, you're never going to go wrong with mathematics. If you're in modern technological science, computer science, chemistry, biophysics, physics, engineering, you name it. That's for all my classes, whether I've taught you at UWM or whether I've taught you at MATC, okay? So right here, let's take the 65 and go here and go here. Let's take the 65 and go here. Formally, in the most formal sense, this looks the most like A plus BI. Real, purely real, plus real times imaginary. Here's real, here's the imaginary. The best. This kills a whole bunch of birds with one stone. We also know how to multiply. We know how to divide too. We were able to do this and know how to divide, so that's good. Looking pretty good in that regard, you guys. Let me keep going. Let me just figure out how I'm going to do this. Let's see which of these markers actually work. You know how that goes. So, and it's certainly nobody's fault if we don't know something right now when we're trying to prepare for something. This stuff works no matter how you're doing it, you guys. Don't even worry about that. How we got to do this at the time that I'm writing this, you know, right now, July, about to go into August of 2020. Obviously, there's something going on in the world that we're dealing with right now. So we're going to make it work. This stuff that I'm showing you, anybody watching this, if you want to know mathematics, hopefully this is going to help you. You're never going to go wrong with more mathematics that you learn. Nobody regrets learning more mathematics if they're in any kind of technological field. Even if you're going into, even if you want to be a physician, it's good to know mathematics and how things relate as far as statistical analysis might be concerned, and other aspects of what goes on. There's always a use for mathematics in technological science. We'll see exactly how they want to play it at various places where I teach, especially at MATC. UWM, I've got a strong feeling, strong idea of where I'm going to go because I've done it in the past with this particular, with the class and stuff. But the math is the math. Who cares? You could be learning this on Mars. You could be learning this 100 years from now. This math doesn't change. Don't ever cheat yourself. Know as much math as you can, no matter what course you're taking. If it's a technological course, mathematics, chemistry, physics, engineering, you name it, the more math you know is always going to help you. Always going to help you. Let's proceed further. right, guys. You see what else I could say, guys, related to this. And like I said, I can always come back and hook it around a little bit. They talk about solving certain problems, you guys, vis-a-vis some of the stuff that I'm talking about. So there's just a lot can be said here, I guess you could say. Just trying to think of the best way to say it. They've got a number of things you can do to solve various problems, and I'm going to get into other stuff too. I may not be able to finish everything I want today, but I can hook around and get a lot of the stuff that I need to get done. Let me talk to you about the solution of problems. I think I just want to kind of do some major stuff here, and then kind of hook around and do some other stuff, and we'll see what we can do. I'm kind of a little bit in the handout that I've given to you guys that you have online. I'm kind of going a little bit all over the place with it, and then you'll see that it's all there. I mean, when you look at the stuff I have shown you how to theoretically do things should get you to where you need to go. We'll talk. We will talk more. I'm going to hook around and get some more things done here. There are a couple things. There are a couple problems in the handout that aren't that good. And anybody can make a mistake. That's not really, whatever, things happen. Let me write it the way it should be written, and we can kind of take it from there. There was like a problem, number 21. I'll show you how they wrote it, and I'll show you how they should have written it. And again, guys, out of about 300 problems, if a couple problems are off, I think you're doing pretty good. I mean, I probably wouldn't be able to do any better. I'd probably do worse, you know. So it's not a condemnation of anybody in that regard. Everything I say here is not a condemnation of everybody, of anybody or anybody. We all got to get this thing right, and we got to do it right. And we're all and without working together. If I didn't have this blueprint of what they had, this would be a hard thing to put together. So they did a wonderful job that did this, and you guys can make use of it. As I said, there were some very hardworking people at MATC that put this together, and I'm fortunate enough to look at it and be able to solve it and work on it. They wrote something like this. That right there doesn't really get you. You can solve that, but it's not. It's kind of there's no solution to this. Here's why there's no solution. Let me just say there's no solution, and then let me rewrite it in a way that I think, that's just my opinion, in a way that I think would have been a better way to write it. If you're writing this right here, 9 plus something would have to equal 0. 9 plus what number equals 0? That's an important point. Let's try it again. 9 plus something equals 0. 9 plus negative 9 equals 0. The problem is, all square roots are greater than or equal to 0. You don't use, the square root of 81 is not negative 9. I know that negative 9 times negative 9 is 81, but that's not how they define it. The square root of 81 is the positive, is the positive root. The square root of 81 is 9. There is no real number that has a square root that's negative. Negative 9 and positive 9 would give you 0. I get that. You're not going to get negative 9 out of there. The answer to this problem is no solution. That's where they're going there. They did it twice. I wish they would not have, but it can happen sometimes, okay? A good way to maybe make one of the problems is make one of them positive so you have no solution, and then write another problem, write something like that, and you're guaranteed a solution. And maybe that's a little more enriching. So here we go. As you look at this, solve that. Why don't you add a positive 9 on each side? Add a positive 9 on each side. If two things are equal, Okay, I added a positive 9 on each side. If two things are equal, they remain equal if you do the same thing on each side. Now, if two things are equal, do they remain equal if you do the same thing on each side? Yes, we already just said that. Why don't you take this? Why don't you square each side? The square of the square root, let's talk about that. That's kind of an interesting point in its own right. If I had x to the 1 over n, and I took it to the n power, that's the same as putting the n power inside and putting the 1 over n over here. Guys, don't you multiply exponentiated quantities? If you're exponentiating an exponentiated quantity, don't you multiply the exponentiated quantities? The n's cancel, and you got it to the 1. It gets you x. Are you telling me that x to the 1 over n, which is the nth root of x, x to the 1 over n, which is the nth root of x, taken to the nth power, the nth root of x exponentiated to the n power is x. It's the same as x to the nth root of it. What number times itself n times will give you x to the n? That's what the nth root of x to the n is, that number such that if you exponentiate it to the n power, you get x to the n. It's x. So if you square a square rooted quantity, you get if you square a square rooted quantity, you get the original quantity. If you square this, you get that. Why don't you add 19 on each side? Okay. We're not done, but here you have to be extremely careful. You have to be extremely careful here. What number squared would give you 100? 10 squared is 100. 10 squared is 100. The quantity negative 10 squared is also 100. Both solve it. Now you can do that. You could say, well, how would I actually do this? How would I want to look at that? That was actually a bank shot, you guys. I should set up another camera so you all can see that, right? Okay. So let's keep going. Why don't you subtract? Is that visible pretty good? Yeah, not great, but that's all right. This one should be good. You subtract 100 on each side. Can you do a factorization? Isn't that 110 squared? Can't you do a difference of 2 squares? What would make this guy equal to 0? What would make that guy equal to 0? X equals 10 or x equals negative 10 works. Okay? So those shots I missed, guys. I threw them both and tried to do a bank shot and it was no go. So these two, and that would solve it. That would solve it. X equals 10, x equals negative 10. Is that even visible? Yeah, not great, but hold on to it. Okay. So let's do another one. Let's look at problem number 24 from the old practice exam number 3. And let me keep going like that. and maybe kind of figure out what's happening here when we do that. Some of these I've already done. Some of these problems, I kind of made up my own problems just now with you guys, and I already did them, so I don't have to do them. I mean, you already got the blueprint of how to do it on film, so you can do it. So your problem number 24. All right, guys, see what I can do. Well, this one's a good problem, I think. This one's a good problem. Hopefully this is a good marker. Let's see what we got here. Okay, it's not too bad. Working okay. X equals all right, so we got something like this. How do you want to solve that? I want to solve it the exact same way I've been solving everything. Get whatever I want to get on one side or another to kind of simplify matters, and then do the same thing on each side of the equation. You're always doing the same thing on each side of the equation. Algebra is an ancient process. You know, in the Middle Ages it was very, very highly developed, but before that it was done as well. It is the foundation of so much of what goes on in mathematics. You're not going to do great mathematics without a strong control of the algebra. You've got to know the algebra. I've been emphasizing that in every video we got, guys. Let me add 4 on each side. Parentheses there. Let me leave this guy here. And there it is. You're looking at something like that. Excuse me, guys. Let me make sure it's good here. All the cleaning fluid I put on there, guys, it's doesn't always hold up too good. Can't really write on it sometimes. Here we go. If two things are equal, they will remain equal if you do the same thing on each side of the equation. If you take the quantity x plus 4 and multiply it by the quantity x plus 4, you get x squared plus 8x plus 16 equals the square root of something squared. You get that right there. Let me subtract 18x on each side. Let me add 9 on each side. X squared plus a negative 10x, or minus 10x, plus 25 equals 0. Or plus a negative 10x. Doesn't matter. You can look at this thing and always come back to the bread and butter. Ax squared plus bx plus c equals 0. x equals the opposite of b plus or minus the square root of the quantity, b squared minus 4ac, the whole thing over 2a. The quadratic equation can get you out of everything that has a quadratic function in it. If there's a quadratic function set equal to 0, the quadratic equation can get you out of just about everything. Not easy to deal with sometimes, not convenient, but it'll always get you through it. It'll always get you through something. So you're looking at that. I can do that. I can make this guy, A, I can make this guy B, I can make this guy C, and go for it. Got a better idea. Can I do a factorization maybe? X squared minus 10x plus 25 equals 0. Is it true that x times x is x squared, and 5 times 5 is 25? And if you put negative 5 times negative 5, it's also 25. Negative 5x, that's negative 10x. You're done. What solves it? What value? Remember, 0 times something will give you 0. What makes this guy 0? X equals 5. What makes this guy 0? X equals 5. Well, Gauss was right. Two solutions happens to be a double solution. X equals 5, X equals 5. You can just say X equals 5. Okay? So that's some of what's going on there. I did the stuff with the eyes, I guess you could say. They had one where they got one here, they got a couple here. I'm sorry, I'm jumping around a little bit on this thing, guys, but again, you got it on film, you can kind of pick and choose where you want to go with this stuff. Eventually you want to get all of it, obviously, but they're saying something like this: why don't you get me the square root? You know, why don't you get me the square root, they're asking. So with this one right here, let me ask you a couple questions. Is 120 times a negative 1, 120 times, is just, here's a square root is square root. Here's a square root, here's a square root. Is 120 times negative 1, negative 120? Sure is. Let me ask you something else. Now again, I could have solved the equation that I just did earlier. Forgive me for digressing a little bit, guys. I could have solved using the quadratic formula. Here's the quadratic equation, and here's the quadratic formula. How to solve it. I could do that, or I could do factorization. They got some other tricks as well. Completing the square. I guess I'll cross those bridges as I need to cross them. Typically what I've done, and again, I don't know how they're going to do. For those of you in my MATC class, I'm not quite sure. I'll know in a couple weeks how they want me to proceed with this stuff. Typically what I've done is, as long as you had the right answer, as long as you knew what you were doing, I didn't really care about what method you used. Short of cheating, I typically don't care how people solve problems. But now, I might be asked to do something different as far as the MATC aspect is concerned. For UWM, I'm a lot more flexible with that. As long as nobody's cheated, I don't care how you get answers. I'm pretty old school like that. As long as you know what you're doing, I'm not going to tell you how to think. Be fair, don't cheat, get the right answer, do it your way, any way that's easiest for you, and I'm happy. So you know that. So we got all this right here, guys. Before I take care of that, let me do something here. It's kind of a takeoff of some of the stuff I did earlier. Remember the laws of exponents we were kind of talking about? Let me throw, for the laws of exponents, let me throw roots in there. And let's talk about it. It's a pretty important point, actually. All right, guys. Well, you saw me say some things earlier. Let me keep saying them. Let me say them a little differently, I guess. X to the 0 is 1. X to the 1 is x. If you were multiplying two exponentiated quantities, and this is kind of a different dynamic now, guys. This is kind of weird. Not sure exactly how I want to say it. Let me talk to you a little bit. If you had a times b to the n, that's equal to a to the n, b to the n. We already talked about that. If you had a over b to the n, that's a to the n over b to the n. Okay, what if you had this then? Instead of n, what if you had 1 over n? You'll allow me to say that. It is the exact same, it is the exact analogous procedure. If you had a over b to the 1 over n, you got a to the 1 over n, b to the 1 over n. Absolutely. May I ask you a question? Didn't we say that anything to the 1 over n is the nth root? The nth root of a product, the nth root of a product is the product of the individual n roots. The nth root of a quotient is the quotient of the nth roots. These are completely analogous. They're not analogous, they are identical. You saw me go here at a different time. Okay? You saw me go here. You saw me go here at a different time. I'm saying anything on top like this, if there's a product, you bring the thing on top and you can bring it inside. If there's a quotient, something on top here, you can bring it inside. For the record, 1 over n, if it's a natural number, this product to the 1 over n, this product to the 1 over n power is this product, the nth root of it. The nth root of the product AB is identical to the quantity AB to the 1 over n. The quantity A over B to the 1 over n is identical to the nth root of A over B. Which is, so what are we talking about? The exponentiation of a product is the product of the individual exponentiations. The exponentiation of a quotient is the quotient of the individual exponentiations. It's true over there, it's true here with fractions as well. In fact, if you had a b to the m over n, let me kind of figure out how much room I got here, guys. You had a b to the m over n. That's a to the m over n, b to the m over n. If you got a over b to the m over n, it's a to the m over n divided by b to the m over n. Absolutely. Where's the moral to the story here? Well, you're seeing it all over the place, actually. The exponentiation of a product is the product of the individual exponents. The exponentiation of a quotient is the quotient of the individual exponents. That follows in an analogous fashion. The root of a product is the product of the roots. The root of a quotient is the quotient of the roots. Hugely important. This thing right here, how does this work? It works the way it always worked, guys. You got AB to the m over n, you got AB, let's say you got the nth root, the whole thing taken to the m. That's the same as the nth root of A taken to the m times the nth root of B taken to the m. You saw me, forgive me for not going into it again, you saw me do that. Didn't we say that this whole thing plays out? How does this thing play out? Well, let me go. Maybe this helps. Go AB, the whole thing to the 1 over n, the whole thing there to the m, which is this AB, the whole thing to the m, then the whole thing to the 1 over n. You know, here's m, here's 1 over m. I'm sorry, here's m, here's 1 over n, here's 1 over n, here's m. It doesn't matter. You saw me do that. I did it with x, but I can do it with anything. Basically, this stuff can all be broken out. Now, could you have written this a different way? You better believe you can write it a different way. You can go AB, the whole thing to the m, and then get the nth root. What does that mean? Well, you take a to the m and then get the nth root, product of the nth root of b to the m. That's the stuff we were talking about earlier, guys. We talked about x to the m over n, and that's x to the 1 over n, whole thing taken to the m. That's x to the m, the whole thing taken to the 1 over n. X to the m over n was the nth root of x, the whole thing to the m, or the nth root of x to the m. That's all it is. So if they were to say to you, you know, hey, AB to the m over n, it's the same argument. It's AB to the 1 over n, the whole thing taken to the m, or AB to the m, the whole thing taken to the 1 over n. I'm not trying to beat this thing into the ground, guys, but you know, once you do that, once you got this here, what is that? There's your nth root of a times b taken to the m, or there's AB taken to the m, and then get the nth root, please. You know, sure. In all instances, we showed it here. We showed it here. And what does that mean? You know, I mean, we said that, first of all, we said these are equal. Let's get that straight. Let's get that really straight. This and this are mathematically identical. You've got this. This and this, they're mathematically, the end answer is identical. What's going on in the interim is different. And yet they're equal. You can prove that they're equal. And they're identical. These are identical, as are these. And, you know, these are identical to one another. And, you know, each one of those is equal to this product. Each one of those is equal to this product. So on and so forth. So, is there a moral to the story here, I guess? Well, there's a lot of moral to the story here. There's a lot of it here, guys. I can't, you know, again, I wish we were in person. Wish we were in person more. But for our purposes, go right there and solve it right there for that one. Again, guys, you know, and the same thing going on right here. If you had A over B to the M over N, here we go. To the M, the whole thing to the 1 over N. A over B to the 1 over N, the whole thing to the M. What's that? Absolutely. A lot here, guys. I mean, it's easier than you think. You know, it's not going to be that bad. But you know, you've got access to the notes. You're looking at it. You're looking at books and stuff like that as we need to do it. But I think we're good. Okay. The big moral to the story is whether you're talking about, you know, I'm going to take it back. All of this is a big moral to the story. It's good to know all of this. I told you guys, I don't care what class you're taking, who your teacher is, or what you're studying. The more mathematics that you know, if you're doing anything in the technological field, and so much involves that these days, the more mathematics you know, the better off you are, period. So it's all important. It's all important. And that's why this is posted in different places, you know, between different places. I was luckily given permission to do so, and I think it's a good idea to do so. That's something that I've done. I want any student I have to see this. These when they can. You wish you had more time, guys. As simple as that. What's the moral of the story? This stuff works both ways, you guys. The nth root frequently is just the second root. The second root, they don't even put it to there. They call it the square root. It means the second root. Could be the third root, the cube root. The third root is the cube root. The fourth root, the fifth root. The nth root. It could be a square root, and then they don't put any number there. The nth root of a product is the product of the nth roots. If it's together like this, you can break it up like that. If it's broken up like that, you can put it back together like that. The root of a product is the product of the roots. The product of roots is the root of a product. The root of a quotient is the quotient of the roots. If you've got the quotient of roots, you can make it the root of a single quotient. If it's together, you can break it up. If it's broken up, you can put it back together. And it helps you solve a lot of these problems. But all of this is important. I mean, I circled in red what we need immediately right here, but all of it is good. All of it is really, really important. And when we get into logarithms a little bit later, I'll come and visit this again. You know, it'll have some kind of application for us when we're doing it. All right. So again, we're looking at this. Let's come back to it. Let me erase this and let's come back to it a little bit and see what we can say. Again, algebra, what's it about a lot of times? Do the same thing on each side. Do it with consistency, mathematical consistency and mathematical rigor. Should be okay. You can do a lot. Okay, guys. I made the move. Negative 120. The square root of negative 120 is the square root of the product, the square root of the quantity, the product, 120 and negative 1. 120 times negative 1 is negative 120. The square root of the product, 120 times negative 1, is equal to the square root of negative 120. Sure, 120 times negative 1 is negative 120. Didn't we say earlier that you can break up the roots? Square root of negative 1 is I. Now all I got to do is find this guy. They don't want a calculator answer on this stuff. For those of you in my math class, they don't want a calculator answer. Calculator answers are good if you're doing an engineering or physics problem oftentimes, but here in the strictest rigorous sense for algebra, they would like you not to do that. Tell you what I'm going to do. 12 times 10 is 120. I know. 2 times 60 is 120. 3 times 40 is 120. 4 times 30 is 120. 6 times 20 is 120. 15 times 8 is 120. I got to start somewhere. Break these up. You can do that, and then go here. It's 4 times 3, 12. Now break it up some more. What am I doing? Well, you're going to see what I'm doing. The square root of 4 is 2. The product of roots is the root of the product. 3 times 10 is 30. I'm not seeing this going any further, guys. What I got is 2 times I. They usually put the I in the middle or put it way far away, but don't put it underneath the radical. That's wrong. Don't, put it far away from the radical. We're talking about something like that. More to come on that. I mean, there's some other ones I want to come back to and kind of look at regarding that. They have some other stuff here, guys. 27 through 32. That stuff I just did. I already did that earlier with the complex numbers. Doing multiplication, doing addition, subtraction, multiplication, and division using complex numbers. You know how to do that. Trying to figure out exactly how I want to proceed on this stuff, guys. At least get a lot of this stuff out of the way, so when I do finally do the review for the final exam, the lion's share of the content has already been presented to you, and I can clean up with some problems wherever it might be necessary. They got some questions they ask, 38 onwards, that are pretty interesting. So let's take a look. Let's try to think of some stuff, guys, to say to you. We'll see how we're going to proceed with this whole process. They've got different ways to solve different problems. Let me throw a few of these problems at you. Let's do them, and we're not going to worry excessively about the whole process here. The big thing here is, if you know how to do the quadratic formula, if you ever draw a blank, the quadratic formula will get you there. Get you to the right answer. When it's a quadratic equation, the quadratic formula is always going to work. If you don't see a good factorization, or if you don't see some other stuff going on, it always gets you there. Let me show you maybe some other stuff right now, but always know, hey, look, Again, the way I teach it is typically don't cheat, work hard, do the problem any way you want if those two things are happening. Short of cheating, I don't care how people get the right answer. Just get the right answer. Typically, that's what I like. That's why I like to see things. However, the more ways you know how to do something, that's a good thing too. More ways you know how to do these problems, you guys, I think it's going to work out to your advantage. All right. There is, speaking of more ways of how to do these problems, they're giving, like, let's say it's a problem like 38. 38 is saying x squared minus 12 is equal to 0. How can you solve it? And they're saying solve using the square root property. There's a lot of ways you could do this problem, guys. I don't know if I don't want to drive you too crazy with the whole process. You can add 12 on each side. You got to this. This answer is square root both sides. It's going to be the square root of 12, but it could be plus or minus the square root of 12. X could be positive square root of 12, or x could be negative the square root of 12. They call this the square root property. One way you can look at it is this guy right here is the same as saying x squared minus is 12 itself the square root of, is 12 itself the square root of 12 squared? Guys, does that look like a squared minus b squared equals 0? I guess I could factor that and write it as a minus b, quantity a minus b times quantity a plus b equals 0. X minus the square root of 12, x plus the square root of 12 equals 0. How do you get x minus the square root of 12 to be equal to 0? X minus the square root of 12 being 0 would be square root of 12 minus square root of 12. X would have to be the square root of 12. What number plus square root of 12 will give you 0? How about negative the square root of 12? So square root of 12 and negative square root of 12. That's a little more rigorous. This is simply the square root property, you guys. That's the property to say. Is there a way you could have gotten out of this thing? I'm not sure how the best way to tell you. You could say ax squared plus bx plus c equals 0. This is 1x squared plus, if there's nothing here, how did I do 3 equations and 3 unknowns? If there was like a term and I wanted to get rid of it, I get 0 times that. 0 times x plus a negative 12 equals 0. 0 times x is 0. 1x squared minus 12 or plus a negative 12. A is 1, b is 0, c is negative 12. If you did the quadratic formula, you don't have to. I mean, you really don't. It's like me saying, yeah, I can climb the mountain. I'll just walk up the mountain backwards. Well, I got a better idea. Just walk up forwards. Better yet, drive up the mountain if you're tired. Whatever. So if there's an easier way to do it, go ahead and do it. That's your business. I told you guys, I don't care. Typically, I don't care how things get done, provided it's ethically done and you know what you're doing. That's it. That's the moral of the story on that one. The opposite of b plus or minus the square root of b squared minus 4ac, the whole thing, over 2a. Yeah, that'll work. That would work. That would work. I did it with factorization right here. And the easiest way in this instance was just square rooting both sides when you got things separated. When you got the 12 over to the other side, you added a positive 12 on each side, and then you square root both sides. That was the better way to go. Okay? Number 40, little different dynamic here, but the same thing. If you want, I'm not going to, you don't have the time to see me do this a whole bunch of different ways, and especially when we don't need to, we're okay. You could do what I'm about to say. I don't really recommend doing it. The square root method is probably a good way to go right here as well. Be careful, but I think it's a really good way to go. You could say, hey, look, Malus, take the quantity x, take the quantity x plus 7, take the quantity x plus 7 and square it. x squared plus 14x plus 49 equals 20. Let's look at it from scratch. See what can we do the square root method on this one? They got this, they got another method called completing the square. And I'm telling you, the quadratic formula will bail you out of all of them if you need it. Depends how, for those of you that have me at the MATC class, how they're going to ask me to approach something. But what works always works, guys. All right, guys. Here it is. We got this right here. How's this going to go? Let's take a look at it. If two things are equal, then they remain equal if you do the same thing on each side. Square root it. Square root each side. If you square root this, you got this. You got the quantity x plus 7. And if you square root this, you got the square root of this. Now this could be positive or negative. Sorry guys, the board is still wet. Plus or minus. It could be a negative number too. A negative number squared gives you the same answer. If I take the quantity negative 10 and square it, I get 100. If I take its opposite which is positive 10. Positive 10 squared is also 100. So we got it to here. What do you say add a negative 7 on each side? Plus a plus or minus. Plus or minus is just plus or minus. Square root of 28 is the square root of the product, 4 times 7. Square root of 4 times the square root of 7. Square root of 4 is 2. Square root of 7 is square root of 7. X equals two answers. What are the two answers? What it means. X equals negative 7 plus 2 square root of 7. X equals negative 7 minus 2. X equals negative 7 plus 2 times the square root of 7. X equals negative 7 minus 2 times the square root of 7. And that's it. Completing this. If you did the quadratic formula, you'd get this. It'd be a little bit of a mess, but you get it. If you drew a blank, you'd get it. You'd still get it. So that's some of the process, I guess you could say. They say some stuff about completing the square. We'll see what we can do. I mean, we try to think here. Good problems here. There's, let's go to problem 43. They call it completing the square to get an answer here. So let me kind of do a takeoff on it. Let me see exactly how I want to do this. I'm going to do problem number 43 on the old practice test number 3. I'm going to do problem number 43. I'm going to do it with a thing called completing the square. And then there's another problem, 44, right after it, that's the quadratic formula. Then the other stuff you can just use any way you want. Again, if it's up to me, you can do anything you want here. Just do it ethically, know what you're doing, get the right answer, and I'm happy. But if circumstances call for, hey, we have to answer in a particular way, we have to demonstrate a particular competency done in a particular way with a particular method, then obviously you have to do that. Okay. That's kind of what I was saying earlier. Again, and that's no, there's nothing wrong with that. Either way, what we're asked to do, we can end up doing it pretty well, I think. All right. Let me look at it. They've got another one right here, guys. So let me see here. This is not, my markers are starting to kind of go haywire on me again. Oh, nice. This is a good marker. Okay, let me see, guys. '43, and I'm going to kind of give it a little bit of a different look, just for a second. 43, they write it in a particular way. And let me go. Trying to think exactly what I want to say here. X squared plus 18x. If they wrote 43 like this, that's fine. they could just as easily have written number 43 in this manner. And now let me just do something and then go right to what they did. So I kind of maybe save a little bit of time. They initially presented it by saying, okay, let's us subtract 58 on each side, or add. Let's us subtract 58 on each side, or add a negative 58 on each side. We got this. Now they want you to do it called completing the square. How do you complete the square? You make it so something's a perfect square. This is all kind of easier done than said. You take the middle term of the ax plus bx, of the ax squared plus bx plus c. You take the middle term, the bx, you take the b, you divide it by 2 and square it. What's 18? What's 18 divided by 2? It's 9. 9 squared is 81. So let me take this guy, and I'm gonna, because this never, it wasn't there. There was a 0 there initially. I'm going to add 81. It wasn't there to begin with. If I add 81 to one side, I got to add 81 to the other side. It wasn't there to begin with. Now, what's this 81? What's so big about the 81? That's a perfect square. It's x plus 9. If you take the quantity x plus 9, if you take the quantity x plus 9 and square it, go the quantity x plus 9 times the quantity x plus 9, add these right here together, it comes out to, I'm thinking is it 23? Sure looks like it, doesn't it? Let me see here. Yeah, 23 right here. Okay, the big move is right here, guys. Divide the 18 by 2, get 9. Divide the 18 by 2, get 9, and square the 9. That's 81. Put 81 on the left-hand side, put 81 on the right-hand side as well. Now square root both sides. Do the square root method here. So you got here, square root both sides. That could be plus or minus. That thing's going to be x plus 9, and it can be plus or minus the square root of 23. Add a negative 9 on each side. 9 plus or minus the square root of 23. In other words, x equals 9 plus the square root of 23, or x equals 9 minus the square root of 23. So that's good. And that's how some of this proceeds, you guys. It gave one here for a quadratic formula, and the other ones they just say go any way you want and get the right answer. So see exactly how I want to go here. And like I said, I can always clean up on a lot of this stuff. If I hadn't done some of the problems the way I want to do them, I can do it when I do the culmination of the thing with the problems that I've done very much so. I don't have to do that much on the review for the old final exam. Review for the old final exam. You don't have to do a lot of those. If we already did those, you know how to look at them and do it. The ones we didn't miss, we kind of hook around and get a good look at them. So let's see what we got here, man. We looked at this. Let's look at some other stuff. Okay, guys. See some of what's going on here. Let me try to get a handle on it, I guess you could say. We'll see how I can do it. See how I want to pace this whole thing. I like to do as many as possible, but whatever. If you do many early, if I do the many early, I don't have to do as many later on, I guess. When I'm doing the review for the old practice final, if I don't do as many, I'm gonna come back and try to talk to you a little bit more about it. They talk about 44. 4y squared minus 5y and of course my marker goes south. Let's see here. So 4y squared minus 5y minus 9 equals 0. Okay, see how that looks, you guys, on my thing here? Yeah, it's okay. It's pretty legible. Looks like it's legible. They say to use the quadratic formula. And let's see what I can say. Um, 4y squared minus 5y minus 9 equals 0, plus a negative 5y plus a negative 9. I know they say x, whether it's x or y, it really don't matter, you guys. Let's see what we got here. We got x is equal to the opposite of b, plus or minus the square root of the quantity, b squared minus 4ac, the whole thing over 2a. Okay? Let me just stop this right here for a second, guys. I'll pick up on this in just a little bit. Give me 1 second here. Right? No, we're going to go right here and get this thing done. So let's go right here. A is 4, B is negative 5, C is negative 9. A is 4. A is 4. I'm sorry, forgive me. Oh, okay, hold on, guys. I just messed this up. Well, luckily we got the equation, so even with the right equation, I managed to mess it up, didn't I? All right, let's see what we got here. B is negative 5. There we go. All right. B is negative 5. 4 is 4. A is also 4. And C is negative 9. Now let's see what we got. The opposite of negative 5 is 5. The quantity negative 5 squared is 25. Uh, 4 times 4 times 4 times negative 9 is negative 144. Minus a negative 144 minus a negative, so 4 times 4 is 16 times negative 9 is negative 144. Minus a negative 144 is 144. That's that. $25 and 144 is 169. The square root of 169 is 13. So kind of keep that in the back of our minds here, guys. So we got this right here. We got x is equal to x is equal to 5 plus or minus. The square root of 169 is 13. And here's 8. And that's it. And that's where you're going to go. The plus scenario is right here. The minus scenario is right here. 18 divided by 8 is the same as 9 divided by 4. Subtract here, you got negative 8. Negative 8 divided by positive 8 is negative 1. A little easier to look at. And that's it. I used x when I should have used y. It doesn't really matter. X and y are identical as far as how they are analogous to one another. Here you can just say that y is equal to x. Y is equal to x. C is C. Okay. Make a long story short. Y equals 9/4. And y equals negative 1. And there you go. For 44, how that stuff plays out, you guys. There's just a lot along those lines, you guys, how you're going to be doing a lot of this stuff. Let me, it doesn't matter a whole lot, guys. The quadratic formula bails you out of a lot of stuff. So let me do 45 real quick as well. I mean, if you know the procedures, if you know how to do one of these problems, you can do all other problems that are very similar to them. I mean, there's a lot of different types of problems there. But if you know how to do each type of problem, you're going to know how to do every problem from that type. So that's kind of that's the good thing about this. You don't need to do, the more you do, the more you practice, the better you get at it, obviously. But you don't have to do 1,000 problems from each type. If you know how to do them, but you got to really know how to do them. I always tell my students that, you don't want to convince yourself you know how to do something when you haven't really worked it. And then when you have to do it live, you can't do it. So you want to make sure that you know how to do the types of problems that you need to do. However much practice is required, go ahead and do it. Once you know how to do a particular type of problem, you can do every single problem from that type. I guess what I'm trying to say. So let's see what we got here, guys. All right, guys. The markers are behaving sometimes, they're not behaving other times. Let's see what we can do. For problem negative 45, now we've already kind of seen something like this. If that's visible for you guys, it's not the best, but so 45 look at something like that. Two things are equal, they remain equal if you do the same thing on each side. If you square each, if the two things are equal, they remain equal if you do the same thing on each side. Here it is, equation, square. Here's the equation, square both sides. Subtract 7x on each side, subtract 60 on each side. Can I solve this using the quadratic formula? You know you can. I've been saying that quite a bit, right? You can always get away, using the quadratic formula to get you where you got to go. Tell you what I'm going to do. Try to think of something good here. Is there a way we can do it with factorization? Yeah, I think there is. 60, the number 60. 1 times 60 is 60. 2 times 30 is 60. 3 times 20 is 60. 4 times 15 is 60. Big deal. If I add and subtract those, I'm not really getting a 7. Okay, I got one. 5 times 12 is 60. 5 times 12 is 60. 12 minus 5 is 7. You guess the way you want to guess, or do the quadratic formula. If you get into trouble big time, do the quadratic formula. X times x is x squared. Here's a 12. Here's a 5. 5 times 12 is 60. I need it to be negative. Well, I'll make this guy a negative 12. That's a bigger absolute value, and I need a bigger absolute value. X times x, x squared. 5 times negative 12, negative 60. Try it again. X times x, x squared. 5 times negative 12, negative 60. 5x and negative 12x and negative 7x. Right on the mark. That's what we want. It's your business how you're going to go about it, guys. Your business how you're going to go about it. But get to it. Set that equal to 0. X equal to negative 5. Or set that equal to 0. Now, we got to be careful. Yes and no. You can't really use negative 5 because the square root of any quantity cannot be a negative. So you picked up a solution you couldn't really pick up here. That's an extraneous solution. 12 works. 12 times 7 is 84. 84 and 60 is 144. The square root of 144 is 12. Well, we just said x was equal to 12. You couldn't really use this guy, though. You had to use that. So you got to kind of watch out there. So watch how they're doing that. You can sometimes pick up, you'll for sure pick up the solution, but you can sometimes pick up solutions that you should not pick up. So on and so forth. They go into it, guys. They get into this stuff a little bit. I'm just kind of randomly going here. I mean, some of these you're just not going to be able to factor that easily. You may want to use the completing the square method. You may want to go just to the tried and true method of using the quadratic formula. Okay, so there's a lot of ways you can go. Let's look at 48. 5x squared minus 3x equals 8. Yeah, you can go here too. I mean, let me see. You're usually better off just doing a factorization if you can pull it off. If not, probably quadratic formula. Okay. So just kind of watch for that. What do you say you subtract 8? What do you say you subtract 8 on each side? Get to here. I don't know. Certainly I can do the quadratic formula, right? You guys know that. Push came to shove, I can go there. Let me see if I can luck out here. If you think I'm guessing, you're right, I am. That's what you're going to be doing too. 5x times x, that's okay though. Within limits, we can do that. 5x times x is 5x squared. 8, 1 times 8, 2 times 4. Now, where am I going to put the 4 and the 2 does matter now, because there's an x here. There's an x and there's a 5x. Let's take a look. I'm trying to get the negative 3 in there. I got a feeling it might be a lot easier than we think. If you put a 1 right here and an 8 right here, you might be good to go. Why? Why is that? 5x times x is 5x squared. 8 times 1 is 8. What do you say you make it negative 8 times x is negative 8x? And positive 1 times 5x is positive 5x. Positive 5x and negative 8x is negative 3x. You could have done the quadratic formula. In the end, it will spit out the right answer. If you'd have done the quadratic formula here, it had gotten you the right answers, but you got to watch out. You got to be careful you didn't pick up something extra. Here, I think you're good. Here's going to be straight on. Basically, you're saying, can you make that guy equal to 0? Can you make that guy equal to 0? So what we have here is 5x minus 8 Let me add 8 on each side. Let me divide by 5 on each side. Sounds good to me. Let me add a negative 1 on each side. That's it. If you'd have done the quadratic formula, guaranteed you're going to get that. If you do it correctly. If you do a lot of things correctly, you can get the same answer no matter how you go about it, if you're mathematically sound in your reasoning. So on and so forth. I mean, there's a lot of stuff, they go into some of the stuff here. We do 49. Trying to throw a curve at you. And there it is. How are you going to do it? It's a lot of ways you can go here, guys. Once again, a lot of ways you can go. You could, I don't, what you advise and what you do. You could make this z squared. You could make it negative 1/5 times z squared equals 1 over 8 times z equals negative 3/40. And then put everything over to one side and do the quadratic formula. It'll work. Do I advise it? Probably not. I probably wouldn't deal with whenever you get a chance to not deal with fractions, then don't deal with fractions in these types of problems. At the end, if you're getting something with a fraction, whatever. Then at the end, if you got a fraction, you got a fraction. I get that. But so let me see what I can do. All right, guys, what's going on? To me, that jumps out at me is this. I could go negative 40. I could go negative 40 times negative 40 times positive 8 times negative 5 and get 1600 and multiply by 1600 on each side to get rid of all the denominators. I got a better idea. Doesn't 8 go into 40? Doesn't 5 go into 40? What do you say you just multiply by 40 on each side? So if you go here, you say, okay, z, let me see exactly how I want to play this. Then you got this. And again, we are doing stuff like that. Don't cancel it once, distribute it, and then do your cancellation. So what do you say you multiply by 40 on each side? What does that mean? That means negative 5 goes into 40 negative 8 times. That means 40 goes here and 40 goes there, so be careful. Negative 8 z squared 40 over 1 times z over 8, 40 over 1, let's see what we got here. That goes in here 5 times. These guys cancel. You got negative 1 right here. Negative 8 z squared equals 5z. Negative 1 times 3 is negative 3. Add a positive 8z squared on each side. You got this. Here we go again. I mean, can we use the quadratic formula? You know you can. You know you can. Trying to think. I don't know. I'm looking right at it. There's something I can do. There's a lot I can do. I don't know if any of it's going to be too easy to look at and get it right. I got a negative 3. Well, I don't even know if I got a negative 3. I got a positive 3 and a negative 1, or a negative 3. I got a positive 3 and a negative 1, or a negative 3 and a negative 1. So I don't even know that. Let me try to get it. Let me try to think about it. Put a 3 right here. Put a 1 right here. You want to leave the 8 in there? Man, 8 times 3 would be huge. I'm not going to be able to get out of the woods. 8 times 1 ain't a bad way to go. Try that. Try 1z right here. Wonder if that's going to work. Look what I'm talking about. 1z times 8z is 8z squared. 1z times 8z is 8z squared. 1 times 3 is 3. Okay, negative 3, don't worry about that. We'll fix it. 1 times 8z is 8z. 3 times 1z is 3z. 3z and 8z is 11z. Yeah, but 8z minus 3z is 5z. That's it. Gonna be doing it. Put a minus right here to get a negative 3z. Here I get a positive 1z. That's the ticket. If you FOIL this out, you're going to get this guy on top. What do you mean? 1z times 8z is 8z squared. 1z times negative 3z is negative 3z. 1 times 8z is positive 8z. Positive 8z and negative 3z is 5z. Positive 8z and negative 3z is positive 5z. 1 times negative 3 is negative 3. Bam, that's it. That's it, guys. That's gonna be the thing that's gonna get us out of this thing. You got 0. Now, if you did you see that? I mean, you could have done some other stuff, and if you didn't somehow do exactly this in the factorization, you're gonna fall short. What happens then? Well, I go to the quadratic formula, and that's gonna give me the right answer. But if the quadratic formula, will be fine. If I set this equal to 0, what number plus 1 gives me 0? How about negative 1? This is stuff I talked about last time. Here, set it equal to 0. Add 3 on each side. Absolutely right. Z equals -1 equals promise. Get the Some stuff is easier than others, I guess. Let me do 53. Thought it was a good problem. A number of ways you could play it. Let me show you. Let me give you the looks. Again, I hate to be sounding like the broken record here, guys, but the quadratic formula for things that have a quadratic function set equal to 0, quadratic formula is guaranteed to get you there if you draw a blank on other stuff. So you can always kind of get your way out of the woods that way. 53 is an interesting one. It looks a lot like 52. 52 and 53 are really similar. As I said, if you can do something, if you can do the type of problem, if you can do any type of problem, then you can do all problems of that type. Okay? If you're careful to do what you're doing. They are, 53 and 52 look a lot alike. Let me do 53, and I think you'll be in good shape to do 52 if you need to. The quantity, 3x minus 7 squared, minus 9 times the same quantity, 3x minus 7, equals -18. To try to pull a fast one on you, try to intimidate you on how to do this. I got an idea. There's a number of ways you can kind of play this thing. You notice that this guy is occurring right here and being squared, and the same guy is occurring right here, and he's a linear term. Tell you what I'm going to do. Because you write it like this, just for the heck of it. Watch what I'm about to do, and let me make the argument. Let me make the argument. What have I just done? What I just done was I created an auxiliary variable. Maybe a better way to say it is this. I took the quantity 3x minus 7. I took the quantity 3x minus 7, and I set it equal to y. Okay, well, so what? Okay, I made a little. Am I justified in doing that? Yeah. Well, the quantity 3x minus 7 is being squared. I just said treat 3x minus 7, the quantity 3x minus 7, treat it as y. If you square it, if 3x minus 7 is equal to y, if you square y, you got this. If you square the quantity 3x minus 7, you are squaring y as well. This is also y. Add 18 on each side. I'll show you another way right afterwards. See that? I could use the quadratic formula right here if I wanted. I got a better way. Let's do factorization. Is y times y squared? I know that 1 times 18 is 18. I know that 2 times 9 is 18. I also know that 3 times 6 is 18. 3 times 6 is 18. What are the factors 3 and 6 added together? What do they equal? 3 and 6 added together is 9. Yeah, close. You all make mistakes, right? Let's catch it. Think that'll work. Think that'll work. Y times y times y squared. Negative 3 times negative 6, positive 18. Negative 3y and negative 6y is negative 9y. What value of y will make that equal to 0? What value of y will make this equal to 0? You're not done. You're not done. But you're close. Y equals 3, y equals 6. Ladies and gentlemen, remember this? Y equals 3x minus 7. Let's put y equals 3 right here. Y equals 3. And let's put y equals 6. Add 7 on each side. Let's solve for x. Add 7 on each side. Divide by 3. Add 7 on each side. Divide by 3. Yeah, that's it. At the end of all that, there's your answer. Here's your answer. Could you have gotten that answer a different way? Yeah, you could have gotten the answer. Sure, you could have. Tell you what, I think this is the best way. But, you know, for the record, let's take a look. A couple things here. You saw me do the substitution. You saw what happened. And I'm telling you, you're going to get the exact same answers. We can do, not do. Some of this stuff's not that, you know, it's not obvious. The guesses you make are, you know, you've got to kind of, you got to go hit and miss sometimes. The more experience you get with this stuff, the better you're going to get at it. I'm not doing it because I got any kind of, you know, great ability at it. I've seen this stuff a lot. Once you see this stuff a lot, it's going to be easy. Okay. Okay. Let's take a look. Take this quantity and square it. Go the quantity 3x minus 7 times the quantity 3x minus 7. And you get 9x squared. 21x and 21x is 42x plus 49. That's a lot. Okay, so grind this out, you get this, I promise you. You got a subtraction here. We'll cross every bridge as we need to cross it, I guess. You got a subtraction here, block it off, and just bring the 9 in. Okay, let's see what we got. Already, you can see it's potentially a mess. Just be careful, you know. Got to really watch out now. Add positive 18 on each side. Yeah, the only thing that looks like the past is the plus 18, right? See what we got here. Minus 42x is plus the opposite of 42x. Let's write it like this. 9x squared plus negative 42x plus 49 minus this. Bring the minus inside and hit everybody. Forgive me, that should have been an x right there. Should have been an x right there. Minus 27x. Bring the minus inside, guys. Bring the minus inside, guys, and hit everybody within these parentheses. Don't go all the way to there. Just go here, within here. Minus 27x, minus a minus is plus. All right, well, let's keep going. Let's add everybody together that we can, I guess. Simplify as much as possible. This is 9x squared. Let's see what we got. This is 9x squared. 9x squared, negative 42x, and, well, minus 27x is plus a negative 27x. What's negative 42x and negative 27x when added together? I think it's negative 71. Let me just look at it to be sure here. No, it's new, let's see here. Negative 42x and negative 27x is negative 69x. So plus a negative 69x. So, okay, we've taken care of this guy, taken care of these two. Why don't you add the 49, the 63, and the 18? 49 and 63 is 112, plus 18 is 130. Well, it's a little more manageable. It's a little bit better than it did. So that's an interesting problem. This is what you're solving. Are you telling me if you use the quadratic equation on this right here, if you used the quadratic equation on this right here, you'd get these answers? Yes, that's what I'm saying. That's absolutely what I'm saying. It's absolutely what I'm saying, guys. Let's just make sure we added everything right. We got it here. We add these two, you got 81. 81 and 49 is 130. Yeah, it looks good. Let me just make sure everything's right. Negative 69, you got the other one is 9. Yeah, it looks good. Looks good. All right, guys, let me see if I can There's a lot of guesses here. This guy could be 1 times 9, or it could be 3 times 3. Don't know. Tell you what, let me go 3 times 3. Or do the quadratic formula right off the bat. If you do the quadratic formula, I'm promising you, you're going to get this. You're going to get this. You do the quadratic formula, you're coming right back to this. Guaranteed. I don't know. I'm throwing that thing around. I don't know if it's going to work. We throw 2 negatives in there and maybe make it. You know what? On accident, I did it right. I could have used 9x and 1x, but it wouldn't have got me the answer. My guess was go 3x times 3x. Break up the 9x squared as 3x times 3x, rather than 1x times 9x. 1x times 9x is not going to get you there. Okay, accidentally, I think this thing works. Look at it. Here's 13, here's 10. That's its own dynamic. 130 is 1 times 130. It's 2 times 65. It's 13 times 10. It's 5 times 26. Well, it's a lot of things. Let's go kind of in the middle of the road on all of this. 3x times 3x is 9x squared. 13 times 10 is 130. All that is true. How do I know that was a good guess? I don't know. X squared 13. That. At least one of them's got to be 0. Go the scenario of each one individually being 0. They don't all have to be 0 simultaneously. But what if, if you multiply 2 things together and you get 0, either one is equal to 0 or the other is equal to 0. But, they are equal to 0. You got this and you got this. Why don't you add 10 on each side? Add 10 on each side and divide by 3. I think you know how this ends. Add 13 on each side and divide by 3. I think you know how that ends. Absolutely. It's the same thing as this. Same thing as that. And that's how you would do 52. Also, it's the same argument. They write some interesting stuff here. They say some things. Let me see what I can do. Take it from there. What I don't finish today in this particular packet for the old practice exam number 3, I'll kind of tie it in for the review for the final, because all the other stuff I've done well enough that I don't have to worry about it as much. I say, just look at the stuff that we've done up to this point. It looks a lot like the practice on the final. There's no point in doing very similar problems over again if you've already seen them and you got them on tape. You can always go back and look at them. But I may not have time to get into logarithms today. It looks like I won't, to be honest with you. But I can do that the next time I get together when I go toward the tail end of of this whole process. So when I talk about some of the things related to logarithms and stuff like that. Okay. So all right, guys, let me do a few things here. Let's talk about some word problems and some other stuff here, and see exactly how I want to take this, how I want to do this. Like I said, there's some stuff I'm gonna catch up on probably the next time we're together. To be honest with you guys, we'll be able to get there's some stuff I'll catch up on the next time. I think I don't want to take this too far. I guess when I'm doing it right now, but the next time definitely we'll hit a little bit of the conic sections and logarithms and exponents. Should go pretty smoothly for us. For right now, though, let's, as we finish up for today, let me look at problems 54, 55, 56. Some pretty fascinating stuff, I guess you can say, when you look at this stuff. 54, 55, 56 word problems for the old practice exam number 3, problems 54, 55, 56. 54 says the following. Shelley can cut a lawn with a riding lawnmower in 3 hours less time than it takes William to cut the lawn with a push mower. If they can cut the lawn in 7 hours working together, find out how long to the nearest tenth of an hour it takes for William to cut the lawn alone. Okay. So we can say a lot here. There is something of interest here. I'm going to say it and then kind of say where the applications are to some of what I'm going to say. There's some application to it found in various fields. But the way this is said, it says Shelley can cut a lawn. Shelley can cut a lawn with a riding lawnmower in 3 hours less time than it takes William to cut the lawn with a push mower. If together it takes them 7 hours, how long does it take William to cut the lawn alone? Okay, at that point you can figure out how long it takes for her to cut it too. There's some really interesting stuff that goes on, guys, that we can talk about related to this. This reasoning associated with this particular problem the reasoning here associated with this particular problem is pretty fascinating stuff. First of all, you have to work under the assumption when they do work together, they're not talking, they're not getting in each other's way at all. And they start at a particular time, and one person works to their fullest potential, the other person works to their fullest potential, and they finish simultaneously when they're working together, and it takes less time. It obviously would take less time for them to finish if they work together and completely stay out of each other's way. This doesn't work if they get into each other's way. If they're bumping into each other, or if they're talking, or if somehow somebody gets in the way of somebody else. If it's set up in such a manner that they should be able to do this the most efficient way possible without being in each other's way whatsoever, if that's the case, this reasoning does indeed hold. Well, how does that work? Well, do you agree that if they work together, it takes them less time to get the job done? They work together under the assumptions that I just outlined. It will take them less time to get the job done with the assumptions that I just outlined. Okay. How does that work? Well, if they work together and they stay out of each other's way, you add their rates of work together and you're done. In other words, if I can do the amount of time it takes for everybody working together is T, and the amount of work they do, we'll call it W. What's your criteria for W? I don't know. Carrying heavy weights up 100 meters of a building, carrying it while walking the stairs, and whatever, something like that. And I'll add the rates together. I can do twice as much work in the same amount of time as he can do, but she can do 3 times the work that he can do. I can only do twice as much as he can do. She can do 3 times the work that he can do. And we can figure this out. Well, if we all work together and not get in each other's way, it's going to take us less time to do the job to climb up that big building, 100 meters high, and carry the weights. The total amount of work is W. The amount of time it takes for all of us working together is T. That's equal to, let's say there's 4 of us, or let's say there's N of us working together. I can get the job, I'm person 1. I can get the job in time, I can get the job done by myself in time T1, by myself. The other person can get the whole job done in time T2. That's my rate of work, that's his rate of work. This is her rate of work. And there's N people, there's N people, each one can do the job in a different amount. They might all be able to do it the same amount of time even. Doesn't mean that T1, T2, T3, and and Tn have to be different. They can be equal amount of times. Fascinating. If you divide by W on each side, divide by W right here, you get 1 over T. Divide all of this by W, the W distributes and hits all of these, and you get this. Fascinating. That's for N people. If the N number of people is just 2 people, then you got this. 1 over T equals 1 over T1 plus 1 over T2. Yeah. If there's 3 people, it's this. All the way, blocking off the other one. If there's N people, let's see however many it is. Okay. Now what? Well, let me use this one. This is the special case we're doing. We're talking about her, we're talking about him. Let's say the amount of time is X. Okay, so what we have Shelley can cut a lawn with a riding lawnmower in 3 hours less time than it takes William. So I'll tell you what. Let's say Shelley is T1. She can do the job in X minus 3, and William can do the job in X. X amount of time. She can do it 3 hours less than it takes William. Together, they do it in 7 hours. That's all it is. You go 1 over 7. 1 over this is it. You're going to solve this. How do you want to solve this one? Well, first of all, you can't have x equals 0. And I know they can't do it, and they can't like snap their fingers and make it work. So x is not going to be 0. X cannot be equal to 3. 3 minus 3 is 0, not allowed. 0 is not allowed. 0 is not allowed here, and 3 is not allowed here, because each one will be 0 on the bottom. Why don't you multiply each side by 7, x minus 3x, multiply that on each side. Does 7 go into here? Yeah. 7 goes into here. Take this guy and go here and go here. Do it very carefully. X minus 3 goes into here 7x times. And x goes into the same thing. Don't truncate it after you did the cancellation. This guy goes into here 7x times. X goes into here. I mean, this went into here, yes. Now start over. Leave him as is, untouched, and bring it over here. You got over here. This is 7x. This is 7x minus 21. This is 14x. Let me subtract 14. Let me subtract 14x on each side. Let me add a positive 21 on each side. This looks kind of rough. I don't think I'm going to get out of there with a 17. The 17 with the 21 present there, I'm probably going to have to use the quadratic formula on that one. Probably got to use the quadratic formula on that one. But this is going to solve it. You're going to get 2 solutions. Sometimes the solutions aren't realistic, though. So we don't know that. I mean, we got this. We're saying, okay, x squared plus a negative 17x plus 21 equals 0. There's a 1 right here. Here's an A. You know where I'm going. Here's a B. Here's a C. A equals 1. B is negative 17. And C is 21. Yeah? Okay, here we go. X equals, who's X? X is William. I'm sorry, yeah, X is William because she does it in 3 hours less than Williams does. Shelley can cut a lawn. Shelley can cut a lawn with a riding lawnmower in 3 hours less time than it takes William to cut the lawn with a push mower. If they can cut the lawn in 7 hours working together, find how long to the nearest tenth of an hour it takes for William to cut the lawn alone. We'll find everybody right now. I mean, at the end of this, it's got to be reasonable though. Let's see what we got. It's got to be reasonable. We're finding X, so we're finding what William does. William takes longer. Shelley takes 3 minutes. Shelley takes 3 hours less than William does. This is Shelley's time. This is William's time. Shelley's time by herself. William's time by himself. Working together, it's 7 hours. Okay, and that's how we did all this. And that's how we played it right here. Okay, I mean, it shouldn't be, pretty straightforward. You've got negative 17. You got the opposite of negative, and I don't have a calculator on me. I'm going to go with what they gave in the answers there. It should be okay. Plus or minus the square root of negative 17 squared minus 4 AC over 2A. The opposite of negative 17 is 17. The quantity negative 17 squared (289). What do we got here, guys? We're looking at it for AC minus 84. What is that? 4AC is 4 times 1 times 21 is 84. A little bit of a mess. 2A is 2. X equals 17 plus or minus the square root of 205 over 2. There's two solutions. I don't know that they're both going to be valid on that. What you end up getting, again, guys, unfortunately, I don't have the calculator, but that's all right. We've got the procedure totally under control as far as that's concerned. What's going on here? Well, they got 15.7 hours on that. Let me just kind of show you the logic. The 15.7 hours they got on the plus part. It's going, like I said, I don't have the calculator, guys, so I gotta kind of I gotta walk you through this in a little different manner. They're saying that the one that we can accept, X is 15.7 hours. That means Shelley is 3 hours less than that. 3 hours less than that, that's 12.7. Forgive me. But this is the guy we're looking for. This is the guy right here. So right here, we got to talk about this. This is actually pretty important. Even though I don't have the calculator as I go through this, doesn't matter. 15.7 hours, where did that come from? It came from this guy right here. The square root, what we got here is the square root of 205 is going to be 14 something. 15 to 14 something, 15 something, whatever. 14 something and 17 divided by 2. 14 something and 17 is 31 something. Half of 31 something is going to be the 15.7 that they're talking about. On the other side of that, if you subtract 14 something from here, it's going to be 2 something. See, you can't, Williams got two solutions, but the realistic solution is 15.7. The square root of 205 is 14 point something. Plus 17 is 31 point something. 31 point something divided 14 point something plus 17. 14 point something plus 17 is 31 point something. Half of 31 point something is 15 point something, so to speak. 15.7. True, it's an answer. If you take, that's if you do the plus. If you go 17 minus 14 point something, you got 2 point something, and you divide it by 2, you got 1 point something. It doesn't work. Here's why. If this was 1 point something, if this is 1 point something, what's 1 point something minus 3? A negative time. Doesn't work, it's not realistic. So you can't really accept the plus. The plus won't work because then Shelley takes a negative amount of time to do the job. It's not realistic. That's not the reality. It's not realistic. So this is what we have on that. Fascinating stuff. I mean, this process. What is important with this, how this all relates later on, depending what courses you guys take, even now, the here and now, for both classes, for any class to which I speak, this is good to know anyway. Just know it anyway. You see this kind of thing in other places. You see this in physics, that relationship. You talk about resistors. 1 over the resistance equals 1 over resistor 1 plus 1 over resistor 2 plus 1 over resistor 3. In other words, the total resistance, 1 over the total resistance is 1 over the resistance of resistor 1 plus 1 over the resistance of resistor 2 plus 1 over the resistance of resistor 3. That it shows up when you're talking about parallel circuits in electrical engineering. Like what is the equivalent resistance when all these resistances are together and they're in parallel to one another? So this has applications all over the place, you guys. For the record, it really does. That was 54. 55, the product of a number and 1. The product of a number and 1 less than the number is 56. Find the number. All right, let's see what that means. All right, let's talk here on this as well. All right, see how this would play out. All right, the product of a number and 1. The product of a number and 1 less than the number is 56. Find the number. So here's the number. And this is 1 less than the number. The product of a number and 1 less than the number is 56. The product of a number and one less than the number. Negative 7 times negative 8 is 56. If I take 8 and subtract 1, I get 7. 8 times 7 is also 56. So each of those numbers would work. Each of those numbers would work. If you subtract 1 from this guy, you got 7. 8 times 7 is 56, just to check it. If you subtract 1 from this guy, you got negative 8. Negative 7 times negative 8 is 56, just to check it. So separately, this could be the mystery number, and x minus 1 would be that guy. Or this could be the number, and 8 minus 1 is the 7. So the two answers are, x could be equal to 8, or x could be equal to negative 7. Eight or negative 7. We just see how they did that. Hopefully they said, I'm sure they said both. Yeah, negative 7 or 8. Negative 7 or 8 works based in the way that I just explained as well. Negative 7 or 8 works. Let's do 56, and I'll finish up for today. Problem 6 is a pretty fascinating problem. Let's look at it. Problem number 56 is saying a car traveled 109 miles on a trip. During 40 miles of the trip, the car traveled through the city and had gas mileage that was 3 fewer miles per gallon than the gas mileage on the highway. If the total amount of gasoline used for the trip was 5 gallons, find the gas mileage of the car on the highway. That's something you got to look at. You kind of scratch your head. It's a great problem. Great problem. Let's do that. How are we going to do this? Again, this is a great problem. 56. Problem number 56. A car traveled 109 miles on a trip. During 40 miles of the trip, the car traveled through the city and had gas mileage that was 3 fewer miles per gallon than
than the gas mileage on the highway. If the total amount of gasoline used for the trip was 5 gallons, find the gas mileage of the car on the highway.
Play this a lot of ways, guys, I guess. It went 100. So let's see here. 40 miles. It traveled a total of 109 miles on a trip. 40 miles of the trip, the car traveled through the city. And had, 40 miles, and what was associated with that was a gas mileage of, we'll call it R for gas mileage. Maybe call it capital R. Capital R, R minus 3. And had gas mileage as 3 fewer miles per gallon. Miles per gallon. And this is like the rate, the miles per gallon. It's R minus 3 miles per gallon as you go through, as it went through the city. The car traveled through the city and had gas mileage that was 3 fewer miles per gallon. 3 fewer miles per gallon than the gas mileage on the highway. So on the highway, it had R miles per gallon. R miles per gallon. And it went a total of what? Total of 109 miles, so 69 of those miles were that way. If the total amount of gasoline used for the trip was 5 gallons, find the gas mileage of the car on the highway. So it used 5 gallons of gas total. So 5 gallons of gas was used total. You understand that 40 miles divided by miles per gallon will tell you how many gallons it used. 40 miles traveled in the city divided by R minus 3 miles per gallon. 40 miles divided by miles per gallon will give you gallons. They'll flip over. 40 miles traveled, and you get R minus 3 miles for every gallon. So, however, that's how many, you get R minus 3 miles for every gallon in the city. R minus 3 miles for every gallon in the city. So how many of those miles go into there? That's how many gallons it took. The other guy, 69 miles on the highway, and that gave you R miles per gallon. Period. That's it. So they're asking here, find the gas mileage of the car. Find the gas mileage of the car on the highway. That's gonna be R. This is highway. So highway, city. I want the highway. Highway is this. City is that. The rest is math. The rest is math, you guys. Why don't you multiply by the product of the quantity R minus 3 times R on each side? And on each side, be careful. There it is. Go here, go there. 5 R minus 3. got? We got 5R. It's pretty fascinating question if you think about it. Every time I look at this question, very, very, very interesting question. The algebra is great. You want to do any kind of mathematics, the algebra's there. I don't care how high you go in the mathematics. You got to look at algebra. You got to have the foundations of the algebra, guys. Very important. That's why we're going through this stuff. 5 times the quantity. 5 times capital R times the quantity, capital R minus 3. This stuff, you know, okay, you do all the cancellations here. And this is what I wanted to do earlier. You really bring them in. Don't ever do one cancellation and think you're done with that particular item. This whole item stays present and goes to both places. If you cancel like this, keep it in your mind that that whole thing is coming over here also. That's what I wanted to do on that. 40 times R and 69 times R minus 3. Ones are on the bottom, so that doesn't do anything. That doesn't mean anything. See what we got here. 5R squared minus 15R. 40R. 69R. Minus 207. What do we got? Yeah, it's looking good. Let me bring this guy over here. Minus, let's see what we got here, guys. Let me add a negative 109R on each side. $207's right here. Yeah, it looks okay. Let me just make sure I've done this right, guys. 109R, right? I mean, yeah, it looks good. It looks, let me see here. Just see really quickly, please. This and this, 109R. You got that. Right. Add them, you get 124. Okay, I don't, okay, let's see how this is going to play out. I mean, maybe quadratic formula will work. You're going to get 2 solutions. You probably got to throw one of the solutions out the window because it's not reasonable. It doesn't make sense with everything that's going on in the problem. Frequently, you end up throwing one of those problems out the window, or you end up throwing one of the solutions out the window. Oftentimes, not always, but oftentimes you do. You see if I can actually luck out here. Here's 5R. Here's R. Here's 0. 3 times 69, right? Let's see here. See what I can do here. The 107, the 207 rather, 9 times 23. So I'm thinking, try to think here. 23, I'm going to put a 9 right here. I'm going to put a 23 right here. I'm just kind of lucking out here when I do this, if I luck out. 9 times, let's see what we got. 5R, let's see what we have here. 5R times R, 5R squared. 9 times 23 is 207. 9R and 23 times 5 is 115. 115R and 9R is 124R. I'll make that a minus. I'm going to make that a minus. I think we hit the jackpot. Set this equal to 0. Set this guy equal to 0. 5R minus 9 equals 0. 5r minus 9 equals 0. That's 5r equals 9. R equals 9 divided by 5. 9 divided by 5 is 1.8 miles per gallon. I mean, there are probably, if it's a tank, yeah, maybe that's what it's got. Here's the problem with this 1.8. If this guy's 1.8, what's 1.8 minus 3? Negative 1.2. Throw it out the window. Doesn't work. Here, r minus 23 equals 0. That's it. That's the answer. If that's the highway mileage, what's the mileage in the city? 3 less than 23 is 20. R minus 3 would be 20. R minus 3 would be 20 for the city, and R is 23 for the highway. And you'd get it. Does that make sense? I think it is. I think it does. Check this out. Put 23 in for R. Yeah, we're talking about the city though. We're talking about the city. If this is 20, if we're talking about the city, we're going to subtract 3. If R is 23, what's 23 minus 3? 20. What's 40 divided by 20? 20 miles per gallon into 40 miles, 2 gallons are used. That's 23. 69 divided by 23. 23 miles per gallon. 69 miles, you need 3 gallons. 69 divided by 23. Remember, we said R was 23. R minus 3 was 23 minus 3, which is 20. 69 divided by 23 is 3 gallons. 40 divided by 20 is 2 gallons. 3 gallons and 2 gallons, 5 gallons. 23 gallons. Absolutely it. Just confirm that, make sure they're agreeing with what we're doing. 23 miles per gallon. It's a neat problem. You're forced, here you're making the move. Miles divided by miles per gallon is gallons. Miles per gallons flips upside down. You got gallons and you got miles canceling. Miles per gallon's here as well. So this is the answer on that one. Absolutely. Great problem, you guys. We'll talk more next time. There's some things we're going to clean up on, but we're going well. Okay, let me get my co-worker so we can process this stuff, and we are done. Thank you very much. Thank you for your time.